Welcome back everyone. Today I will be demonstrating the power equations in polyphase system. Previously you already know the power equations of single phase systems, and you know there are three different types of power. One is average power, another is the apparent power, and the third one is the reactive power. So first of all we will focus on Y connected balanced load. And as a prior knowledge, you should know the Y delta Y connections. Y and delta connection are already covered in previous lectures, and there are some homeworks that was mentioned in previous lectures, and if you do so, then obviously these delta Y and Y delta connection are already covered, I believe. So now this is a Y connected balanced load. So Y balanced because all impedances are equal, all are Z, and let's consider that Z equal to R phi plus minus JX phi. That means that impedance is composed of a resistance and a reactance component. So this could be either inductance and or either capacitance. So now we will calculate our average, reactive and apparent power. So now you can understand that this is a general representation of a Y connected load. So these are the phase voltages V phi, and these are the phase current I phi, and these are three lines. So associated with these three lines there are three line currents IL, and from one line to another line we call the line to line voltage, that is EL. So here this is a balanced Y connected load. Now first of all average power. So from single phase you already know that the average power we can write VI cos theta. So first consider only a single phase. So for this single phase obviously the voltage should be V phi from here to here, that means the phase voltage. So the phase voltage V phi, and also the current in this phase is I phi, and the cos theta, which is the angle between V phi and I phi. So this is the equation of average power. Now if you consider for this resistance only, since average power or real power both are same, so another name of average power is real power, and this real power is basically associated with a resistive components. That's why if you write that V phi equal to only VR, that means only voltage across only that resistance, then you can write theta equal to 0 degree. So now the equation appears VR, then I phi, and then cos 0 degree. So cos 0 degree, you know that cos 0 degree equal to 1. So equation appears as VR into I phi, and then you know that I can write I phi equal to VR over R phi. So then it will appear as VR square over R phi. Again I can write V equal to IR, right? So V equal to I phi and the R phi. So then it will be appeared as I phi square R. So these are different representations, because we can write power equal to VI or V square over R or I square R. So from DC circuits you already know this sort of different representations. So remember one thing, this is VR, that means voltage across this resistance only, whereas this is V phi in the above expression, that means this voltage is the total phase voltage. So obviously there is a subtle difference between V phi and VR. So VR is only this and V phi should be here to here. So whenever you use any equation, observe it closely where it is V phi or it is VR. So I always suggest you to use this sort of equation, because this creates less confusion. Otherwise you need to manually check whether it is VR or it is V phi and other sort of stuffs. So this is the average power equation. Now the total average power. So here if you notice closely, we have a balanced phase. That means all three branches are equal. So we can write the total power equal to PAN, that means A phase, then PBN B phase, and PCN, that is the C phase. Since all phases are equal in load, then we can write that all are equal to, let's say, P phi. That means our previously calculated power. Then the total power appears as 3 P phi. That means our single phase power of each phase multiplied by 3. Again, so it was previously our phase component, that means phase voltage, phase current. Now if we convert it into line component, first of all it is a Y connected load, and we know that for Y connection obviously the phase voltage is equal to line voltage over √3, or I can say the line voltage equal to phase voltage multiplied by √3. We have proved this expression in previous classes. And also for Y connected load, the line current and phase current are equal. So if you put these values in our previous expression, which was 3 V phi I phi cos theta, then it will appear just like this: 3 EL over √2 and I phi equal to IL. Then that √3 and 3 we can write it only √3. So now this is the final expression in terms of line component. So I can write power equal to √3 EL IL cos theta. And also if you want to write another expression, that is 3 IL square R phi. So that is the simple expression here it is shown. So this one. And since the I phi and IL both are equal, so I can write it 3 IL square R phi as well. So this is the average power equation in terms of line components. And now we will focus on the reactive power. So you know that reactive power is similar to average power expression, but here instead of cos theta we have the sin theta. So that's why the expression V phi I phi sin theta. And also you know that reactive power is associated with only the reactive components, that is the reactances. That means this x phi. So if we write here the theta equal to 90 degree, then we have to write V phi to Vx. That means whenever theta equal to 90 degree, that phase voltage is equal to just the voltage along this x phi. So now this expression is simplified at Vx I phi, and then similar to our previous expression we can also write it as Vx square over x phi, or also I phi square into x phi. That means these are different representation, that is V square over z, or I square z, or Vi. So these are different expressions, but I always suggest you to use the first one, that is V phi I phi sin phi. So this will create less confusion. And the total reactive power, just like our average power, so it will be 3 multiplied by that single phase reactive power. That's why now it is 3 V phi I phi sin phi. And again if you convert this phase component to line component, then similarly to our previous calculation it will appear as √3 ELIL sin theta. And also you can write it 3 IL square x phi, and the unit is volt ampere reactive, that is var. Now the apparent power. So you know that the apparent power is just the multiplication of voltage and current. So apparent power is just the V phi and I phi for a single phase obviously, and then for the total apparent power will be 3 multiplied by 3 into that single phase apparent power, since it is a balanced phase. So similar to our previous expression, it is 3 V phi I phi, and again if we convert this phase component to line component, then it will appear as √3 ELIL. And our last expression, which is the power factor. So you know that power factor, which is cos theta we can say, and also it is the ratio of our real power to our apparent power. So Pt over St, and if you divide this, so it will appear as the cos theta, and theta is the angle between the V phi and I phi. So far we have just derived some equations for Y connected balanced load.